Hi, everyone. Hello again. So I'll start again. My name is Gabriela, and I am a PhD student at Delft University of Technology. My main supervisor is Dr. Eva Landsogt, and the title of this paper is Stop Criteria for Preflow Testing of Reinforced Concrete Structures. So first, I would like to give an outline of my presentation. I will start with the background and the motivation. Then I will make a brief review of the existing stop criteria that we use for this paper. That is basically the German guideline and the stop criteria that we found that has theoretical background. And then I will show how we use these existing stop criteria and the results from test, failure test and Preflow test in the Netherlands to verify this. Also the summary and the conclusions, and finally, what's the ongoing and the future research. So first, why Preflow testing? Well, in the Netherlands, just as in many other European countries, many of the existing reinforced concrete bridges were built in the 1960s and 1970s. So this means first that they were designed with different life loads. Nowadays, we have an increase in these life loads. It also means that they are in the end of the service life. So if we combine these two, when they are assessed with the new design codes, they can rate insufficient either for shear or flexure. And we also have to add here the material degradation of these structures. So then the question becomes, is this bridge safe? You can usually assess them through calculations or maybe finite element models. But there are some cases when this is not possible. Sometimes we cannot find structural plans of these bridges, or it can be that we don't know the extent of the material degradation, or we see the bridge and we are expecting additional capacity. So in these cases, a direct and effective method is to perform a Preflow test. So in a Preflow test, you directly apply a factor of life load to the bridge to show that it fulfills the code requirements. However, this load is usually quite high. Is a high load level, and therefore it also involves a large risk of causing some irreversible damage or even the collapse of the structure. So here is where the concept of stop criteria is introduced. It was introduced to guarantee the safe execution of a Preflow test because it provides a warning of you are causing some irreversible damage, or you are changing the behavior of the structure, or you are near the collapse of it. So these stop criteria are usually defined with limits of strain in the concrete, the onset of nonlinear behavior, limits for crack widths or crack development. And what happens is that during the Preflow test, you are monitoring these structural responses. So in Preflow testing, also sensors and instrumentation are very important. And what you do is that you compare these field measurements to the thresholds or predefined limits defined by the stop criteria. So if during your load test, any of these stop criteria is reached, this indicates that the test needs to be stopped and that no further loading is permitted. In codes and guidelines from some countries, you can find prescribed stop criteria for flexural failure. But what happens if we have a shear critical bridge that you want to assess through Preflow testing? You will not find any shear stop criteria in codes or guidelines. This is mainly because shear failure is considered a brittle failure that occurs without any warning and can cause the sudden collapse of a structure. So this is mainly what is missing to define this shear stop criteria. Is also part of my PhD project. And what is missing is that we need to understand the shear failure mechanism of these type of structures that are reinforced concrete slab bridges from the moment that we apply the load to the collapse of the structure. So to define this, we need to gather information or find an indicator that this failure will happen before it happens. What we did in this paper was that we review what is the existing stop criteria for Preflow testing. We chose the one that it can be found in the German guidelines for flexure. And also we focus on theoretical stop criteria for flexure and shear failure, and qualitative stop criteria that is based on the reduction of the stiffness and deformation profiles. So if we do this review, we can find that for flexure in the German guideline, you can find a limit for the concrete strain that is based on a single value of 800 microstrains by minus the strains caused by the permanent loads. There is also a limit for crack widths in new cracks and existing cracks. And regarding the proposals that have a theoretical background, you can find 4 in the literature. One is also a limit for strain that is based on the flexural theory and a limit of the tension in the steel of 65% of the mean yield strength. You can also find a crack width limit that is based on theoretical model for large reinforced concrete members. There is also a limit for a maximum and residual crack width that was proposed by Voss and is based on experiments on specimens reinforced with plain bars. This was specifically chosen because many of the existing bridges in the Netherlands are reinforced with plain bars. And there is also a deflection criterion that is based on the moment and curvature diagram that was proposed by Monnier in the 70s and is based on the decreasing stiffness after loading and unloading. And regarding the shear failure, we can find 2 proposals. Both of them are based on the critical shear displacement theory. This theory is based on the critical opening of a shear inclined crack that is triggered by the critical displacement. This theory also considers that the shear capacity is equal to the sum of the contributions that happen in the compression zone, the double action, and the aggregate interlock. So considering this, Lanzot proposed a limit to this crack width using the simplified expression from aggregate interlock. Aggregate interlock basically tells us that when there is an increase in the crack width, then there will be less contribution from the shear that is produced due to the protrude aggregate. So using this idea and also the limit for the shear capacity given in the Dutch guideline for assessment of bridges, she proposed this limit that already considers also a limit for cracked and uncracked specimens. And there is also a limit for concrete strain at the bottom of the cross-section proposed by Benitez, and is based on the assumption that shear occurs before the yielding of the reinforcement and after the appearance of flexural cracks. Other criteria that we used for this paper was the reduction of the stiffness that is set to be less than 25% of the original stiffness. And this can be calculated from the measurements in the field from load and deflection. We also have the called deformation profiles. These profiles are calculated with measurements of deflections at different points along the span on the transverse direction of the bridge. And what you do is basically you plot this information at each load step, and you try to identify if there is a change in the behavior of the structure. So using these sub-criteria, we use the information and the results from failure tests that had been carried out previously at TU Delft. One of them was a collapse test that was carried out in a bridge that was tested at in two spans at the shear critical position. However, only flexural distress was found. We also had the results of beams that were shown from this bridge that were simply supported and tested under a concentrated load, where we had 4 flexural failures and 1 shear failure. We also had beams that were cast in the laboratory with plain bars, where 4 had a flexural failure and 2 shear failures. So with the results of these, we quantify the margin of safety provided by each criterion. We defined this as a percentage of the maximum load at which each criterion was reached. And here I also want to note that we neglected any crack widths that were smaller than 0.05 millimeters. So in this slide, I present a summary of all the results for all the beams. We have the casted beams and the beams that were sawn from the bridge. One of the beams had been previously cracked in bending. The governing stock criteria, considering the theoretical stock criteria, was the crack width limit for most of the beams. For others were the deformation profiles. This means that these tests would have been stopped between 42 and 70%. I want to note that the residual crack width from Boss' proposal didn't really work because most of these results had a crack width smaller than 0.05 millimeters. And regarding the deflection criterion, it was not able to reflect this effect of the previous bending cracks. Here I present the results from the shear test. We had only 3 results. Each of them is a different case, either a cracked beam, an uncracked beam, or the beam that was sawn from the bridge. For the cracked beam, the strain criterion was reached at 50% of the maximum load. Then for the uncracked beam and the sawn beam, it was reached at 56 and 57% respectively. And the criterion were the stiffness reduction and the deformation profiles. Then for the failure test on the bridge, the test would have been stopped between 62% and 65% of the maximum load. For both spans, the governing criterion were these deformation profiles. And well, additionally, in the Netherlands, proof loading is a topic of interest. So we had data from pilot Preflow tests that have been carried out since 2007. So we have data from 4 bridges that were proof loaded, either because they had some deterioration due to ASR, or because they were found to be either flexural critical or shear critical, so they were proof loaded, either using a Belfast truck as the one that I show in this figure, or with hydraulic jacks. And then, well, these bridges were heavily instrumented in the field. We had information from strains, crack width. I could analyze or quantify the reduction of the stiffness and also plot the deformation profiles. It's important to note that during this field test, no signs of distress or nonlinear behavior was observed. This means that they were a successful test. And we wanted to check if any of the stock criteria that we were investigating was exceeded. And here I have the results. In the top part is for the test in the flexural position. We have the measured strain and the limits, the same for the crack widths, at what was the stiffness reduction. And the result is that none of the stock criteria was exceeded. This is promising and it's actually good because it's in line to what was observed in the field test. So finally, summary and conclusions. Preflow testing is a direct method to assess a bridge. Stock criteria provide a warning of irreversible damage or could even the collapse of the structure. This paper focused on existing stock criteria that has a theoretical background. We use the failure test to check this margin of safety provided by these criteria, and the data from the Preflow test to check that none of the criteria was exceeded. And with this, we propose to have a stock criteria that is divided into flexural failure and shear failure, divided for uncracked specimens and cracked specimens that contain strain and crack width limits that are based either on a theory or a model. We also added the 25% of a stiffness reduction, the deformation profiles, and something you should always check in a Preflow test, the load deflection diagram. And well, finally, a bit of the ongoing and the future research. Even though the results are promising. They were based just in 3 tests that resulted in Shear. So what we are doing now is we are doing experiments on half-scale slabs that represent a reinforced concrete slab bridge. We want to gather information of what happens before shear failure to find this indicator. We want to verify this proposal or propose a new stop criteria that is based on a theoretical model and that is applicable to slabs. We are also paying a lot of attention in the measuring techniques. For these, these experiments, we are using acoustic emission sensors, fiber optic sensors, digital image correlation. And finally, we want to also quantify the uncertainties that come from the measuring technique itself and also from the theory that we are using. So with this, I finish my presentation. Thanks a lot, and please feel free to ask any questions.
Thank you very much, Gabriela, for this interesting presentation. So the discussion is open. There is no questions, written questions for the moment.
Okay.
I have some questions for you.
Okay.
So, yes, I would like first to understand your proposal. So your proposal is to determine a criteria to stop the load test, and this is very difficult, especially for brittle failures like shear, but not only for bending moments when the failure is due to the compression, which is not so ductile, and also could be very brittle. Well, I want to. You have said also that you want to stop the test to avoid any failure, of course, but also to avoid any damage, important damage in the structure. And this is the thing I would like you to clarify, because it is clear that it seems that your proposal is to control the crack width, the degradation of the stiffness, and the deformation. I remember, but how you can be sure that with these limits you are not producing a big damage in the structure? This is my first question.
Yeah, well, that's a hard question. Thanks for your question. Yeah, I think the starting point for any of the, well, at least the quantitative stop criteria, the one that is based in crack widths or strains, is the steel strain. But the challenge with this type of also Preflow tests in existing bridges is that we don't know in what part, let's say, of the diagram we are in. Like, could be that we we don't know exactly at what point. So it could be that we are really near of causing this, could be yielding, let's say, of the reinforcement. So right now what we propose is that in these stop criteria, we provide 60% of the yielding strength we consider in the tension reinforcement. In this way, we are trying to avoid the yielding, and we provide this margin of safety. But the challenge is to really know in what part of the graph, let's say, are we, and with an existing bridge, that's a little bit hard.
Yeah, because in shear failure, you can have the failure due to tension in the web, but you can have the failure due to compression in the web also. And the two failures are completely different.
right now we are focusing just in reinforced concrete slab bridges. Reinforced. So here
you
also
don't have big problems with the compression.
Yeah. The challenge is also what can be measured in the Preflow test, because usually the only accessible part that we have in a bridge is the bottom part, the bottom section. So it's about finding an indicator that can be measured there that will tell us that something is happening in the bridge.
Okay.
I think I have a follow-up question always on this topic.
Yes.
When you talk about preventing damages, then you talk about the opening of the crack width. And I was thinking if you have taken into account the exposure of the structure, if by increasing the crack width, for example, you have a risk of increasing the speed of the corrosion process.
Yeah, we have thought about also like giving a limit due to this like durability, let's say. We can already find in the code, I think the crack width is between 0.3 and 0.2 millimeters to avoid this part. So yeah, it's a matter of combining everything, like the parts that you don't want to produce a failure because of the, let's say, the mechanism, and also to prevent this part of opening further the cracks and then causing some other type of damage. But well, if we can also inject the cracks maybe and try to fix this issue later after the Preflow.
That sounds interesting. I also have another question.
Yep.
I think the presentation was very interesting. And I've done most of my research on plain bars, so I found that this topic particularly interesting. And I was wondering if you were planning to divide the stop criteria based on the type of bars in the bridge. Because, for example, at least in my experience, the behavior of plain bars is quite different. You also have anchorage hooks in many cases, and that really change how the structure behaves, especially for the shear failure.
Yeah, we have actually the slabs that we are testing now. That is actually my project, my PhD project. We have divided into a set of experiments on reinforced reef slabs, and we are gonna start in a few months the part of plain bars. We have also designed slabs that represent bridges that are reinforced with plain bars. We want to also study this difference between having reef and plain bars, and also divide the stop criteria between these two.
Are you planning to consider corrosion damages? I know it's a lot of things together, but since they're old bridges, then you also have corrosion damages.
It's not considered right now, but it's a good idea. So thanks.
Now we have a question here. Have you considered using nonlinear finite element analysis to check the measurements? Thank you for your presentation.
We actually, that was also part of my first year, like before designing the slab experiments, I did a lot of work on modeling the slabs that we're testing now in the laboratory to check maybe not so much the measurements, but what would be the failure, like if it was shear or it was flexural failure, to check at what loading positions we will test. And this part, in that sense, we did do some modeling of these type of slabs.
But normally you don't have all the information in a real structure. You don't have, if you don't have drawings, you are not able to do any
Modeling, yeah.
Modeling, yes. Yeah, you can do some modelings, but non-linear models. So yep. This is a problem, and this is the reason why you use proof tests.
Yeah.
There is another question on the chat that says, what about non-destructive techniques to assess the structural health?
Well, they are but here we focus on Preflow test. The idea is to show that the bridge can carry certain load, certain factor life load. So you need to put the load in the bridge to show this. Of course, this is combined with other type of non-destructive methods that you need to carry out before doing the Preflow test. Before doing the Preflow test, you have to go and check what is the concrete that we have, what are the existing cracks that are already there. So there is a lot of work before going and Preflowing the bridge.
One question could be, what is the role of the sensors you are planning to use for the test? You mentioned fiber optics, you mentioned DIC. Is it for monitoring the test, or there's also a thought about using these methods for monitoring the actual bridge? Like fiber optics is quite interesting.
Yeah, we are checking the possibility of using these let's say promising techniques in the actual test, in the actual Preflow test. It would, for example, very interesting to combine acoustic emission sensors, which are that we really found that has a lot of potential with, for example, digital image correlation. Monitoring the bottom of the slab or the bridge, we can see what cracks are, at least at this stage, we're doing it in a qualitative sense of what cracks are opening, how are the cracks developing, and this can also already be very useful in a Preflow test, I think.
That sounds very interesting, I think.
Farid, you have written a question in the chat. Do you want to ask directly to the presenter?
No, thank you. I think that yes, Gabriela, you replied to my question, so it's okay.
Okay.
Thank you.
So we have 3 minutes. Still 3 minutes. It's a very interesting and difficult subject, but we need to have good estimations or good criteria to stop the load test. It is very important, but at the same time, it is the only way to use this type of proof to try to have more knowledge in many cases in which you don't have any knowledge. You know the geometry, and you know the level of deterioration of the structure, but you don't know the reinforcement, you don't know the details, you don't know the quality of the materials and so on.
Yeah, it's
very interesting.
Yeah, thanks a lot.
So we have still 2 minutes. Somebody else would like to make a question? I have a short one. You know that in Europe and in FIB, especially, we started to use the compression field theory to assess and also to define the shear behavior of our new and existing elements. My question is, in some cases, probably in slab bridges, it is not possible, but in other cases, it should be very interesting to measure epsilon1 and epsilon in the different directions in order to know or to get information to make a retro-analysis to estimate the bearing capacity to shear of the elements.
Yeah.
Can you say something about that?
We actually published a paper about using DIC measurements to measure strains in a pre-stressed girder using the modified compression field theory and the strains that we had measured in the web. So yeah, it's possible for other type of structures, not for reinforced concrete slab bridges, but yeah, it's possible and it's very interesting.
Okay, thank you so much to everybody. And thank you so
Thanks.
much, Gabriela, for your presentation.